This afternoon is Jong Kim from Virginia, and he's going to talk about strong solutions of the stochastic Navier-Stokes equations in R3.
Thank you very much. Well, I'm from Virginia, but I'm not from University of Virginia. I'm from Virginia Polytechnic, so it's different university. First of all, I'm very grateful to the organizers for inviting me to give a talk at this workshop. I feel honored to give a talk at this workshop. I will talk about stochastic Navier-Stokes equations, and we are all familiar with the Navier-Stokes equations. It's one of the evolution equations that have been intensively and extensively investigated for a long time, perhaps since Lee's work on 1930s. So naturally, stochastic Navier-Stokes equations is also a very popular subject. But I'm not going to give anything, I'm not going to talk on anything general, but I will just focus on very specialized topic on stochastic Navier-Stokes equations. I know that there are several people in the audience who are far more expertise on this subject than I am, so I'm not sure whether it is safe for me to give a talk at this workshop, but let me try. All right. Okay, so first of all, why is the Navier-Stokes equation so popular? The answer is immediate. It describes the motion of water, and we all know that water is the most important commodity on this earth for all living creatures, including human beings. So, excuse me. Stochastic Navier-Stokes equation is a Navier-Stokes equation with random noise. Okay, I need a stick. So, U is the velocity vector, and the second term is the convection term. That's the term which causes all the trouble, as we know. And the third term corresponds to viscosity term, and for convenience, I take the viscosity to be 1. And in general, it's a positive coefficient, but it's a fixed anyway, so it's not a big deal. P is the pressure, scalar function. And the right-hand side is a typical form of random noise. It's not the general form, but it's a reasonable form of random noise, as I understand. And eventually, I'm going to assume that these Fj and the Gj's are Lipschitz continuous functions, as usual. And I'm going to consider this equation in the whole space, three-dimensional space. And of course, this is a divergence-free condition and the initial condition. Initial values will be random variable. Right now, it seems like deterministic, but that includes a deterministic case anyway. And here, Bj is a typical sequence of mutually independent standard Brownian motions. All right. So this stochastic Navier-Stokes equation has been very widely investigated. There are many results on various different subjects. So the issues I will address today is this. Local existence of a strong solution. Here I have to be careful. First of all, I do not consider martingale solution. A stochastic basis is given and fixed together with the Brownian motions. And I keep them to the end. I do not change it. And then what do I mean by strong? Well, this terminology, I'm not sure whether I can use that terminology or not, but it's okay. But it can be still a little bit misleading. By a strong solution in the deterministic Navier-Stokes equation, typically it means a solution with the initial value h1. But I will work with a lower order. So I'm not sure whether I can use this, but I believe it's okay to use this terminology strong, because in this lower order regularity, I still have a uniqueness of solution. Of course, it's not my result. It's already known for the deterministic Navier-Stokes equation. And then the second issue is that global existence of the strong solution. For the deterministic equation, we know that smooth solutions exist globally if the size of initial data are sufficiently small. It is well known. And my curiosity was, can you carry over this result to the stochastic case? And I have some positive result, but not a general form of a random noise, but for special form of a random noise. Then I have some result. That's what I'm going to present today. Okay, so my analytical procedure is heavily dependent on the known results from deterministic equations. So why don't I review the relevant deterministic equations first? Okay. All right. So left-hand side, the right-hand side is 0, no random noise. This is a no non-homogeneous term. It's just a 0, and it's a typical Navier-Stokes equations on the whole space. I believe there are billions of different results on this equation since 1930s, and a lot of results. But I will just point out one relevant result I used. That is due to the Kato and Fujita. What they did was they lowered the regularity of the initial data. They could work with the initial data with the h1/2 instead of h1. So it's a larger function class. Then they were able to prove the local existence of solution together with the uniqueness of solution. And to my knowledge, h1/2 is the so far the best regularity which guarantees the uniqueness of solution as far as the L2 setting is concerned. There are two papers. The first work appeared in the Italian journal. I think it's from University of Padova. And then, oh, by the way, I think in the first paper, the name Kato appeared first, even though the alphabetically F comes first. I don't know. And later on, the name orderings have been switched. And the second paper is based on the first paper. In the second paper, they provided more technical details and some more regularity results. Okay, so that is the results on deterministic equations I'm interested in. And then, oh yeah, right, their results is this. If you know is this subscript sigma means divergence free, okay? So, but the order is 1/2 instead of 1. It's the 1/2 is the order of user Sobolev space in L2 setting. If you know is in this function class, then they could prove the existence of solution in this function class. And besides, if the size of the initial data is sufficiently small, then the solution exists globally in time. That's the result. And my goal is to extend it to the stochastic case. By the way, these results have been recapped in the monograph by the French mathematician. This is a very nice book and also quite recent. It starts with modern analytical tools to study the Cauchy problems for the Navier-Stokes equations, and not only that, one section is exclusively devoted to the results of these papers. And unfortunately, I do not attempt to pronounce this French name. One time in the past, I attempt to pronounce some French name and I become a laughing stock. So this time I would not. But I believe that there are several French mathematicians, and somebody can pronounce this name for me? Oh, please speak aloud.
Navier-Stokes.
Thank you. That's the way. Okay. So. Yes?
What is sigma?
Oh, this sigma, the notation is for divergence-free vector pairs.
Pardon?
Divergence-free vector pairs.
Oh, okay.
Yeah, divergence-free. Yes. All right. So let me come back to the stochastic Navier-Stokes equations, and compared to other topics on stochastic Navier-Stokes equations, there are not that many reference works. So I will just put up papers which are concerned exclusively with strong solutions. Where some authors are already in the audience. And when I wrote up the paper by, I don't know how to pronounce, Kapinski and Pessin, and he was a previous speaker. That was the, I apologize for pronunciation. This was I thought that this was the only available reference, but then later on, the referee pointed out some other references, and I was a little bit embarrassed. But I have to confess that I still don't have an access to the second reference and this fourth reference, so I do not know what the results are. But I presume that their results are different from mine. Not only that, I found this last reference just a week ago accidentally. Yeah. But it's available, so I had no problem downloading that paper. The result is different from mine. So. Okay. All right. So my immediate goal is to present the main results, but for that I have to tell you what the assumptions on the random noise are. So, all right. My own memory is so bad, so I have to go back to the previous stochastic form of Navier-Stokes equation, and now I'm gonna, yes, that can help. Yes, thank you very much. Oh, okay, all right. So I'm gonna make assumptions on FJs and GJs. It'll be just a standard easy conditions of Lipschitz continuity. All right, so I assume that this Fj, so it's a sequence, is a given continuous maps from this function. Oh, by the way, I didn't say that. Even though Kato and Fujita obtained the result in the H1/2, I need a slightly positive alpha. You will find out that it is necessary for my technical procedure to get an estimate of stopping time. I mean, the random time on which the existence is guaranteed. So I need alpha positive. It can be very, very small, but I still need it positive. So I fix it. Alpha is a certain number between 0 and 1/2. If alpha is 1/2, then the strong local existence is already known. Okay? Yeah. So I will just restrict alpha between 0 and 1/2. All right. Then the assumption on Fj is this. It's a standard Lipschitz continuity here. And then this gamma is a very, better be very small. I say that the C is some universal positive constant, but it's a little bit cheating because it depends on the viscosity, and I assume that it's 1. So after you fix it at 1, then I may say it's a universal, but it's a little bit cheating. Okay. All right. And then under these conditions, assumptions, then I have to define the definition of a solution. It's long and it's boring, but I hope you don't mind. Okay, so excuse me, the is a given initial data, and it's in this function class. And oh, by the way, f is the yeah, I assume that the stochastic basis together with the filtration is given. So when t is equal to 0, that's in the one of the filtration family f measurable, and the pair. So you might wonder why this tau is a stopping time, why tau is included as a part of the solution, because solution, the function u satisfies the Navier-Stokes equation only on the random time interval from 0 to tau. That's the reason. So this is a user condition. So tau is actually the limit of finite stopping time sequences. And then what is tau n? Tau n is given by this condition. And the basic tool for the proof of existence theorem is cutoff function and stopping time. And the previous speaker already used it for the nonlinear Schrödinger equations. That's a very powerful tool. So the role of this stopping time is that if a solution becomes too big, you stop there. From that moment on, evolution does not occur. You just stop there. And that's the meaning of the stopping time. And so the function satisfies the original equation only up to that stopping time. Beyond that, even though it is defined, we do not know whether it satisfies the original equation or not. Okay, so that's the meaning. And then this tau is this tau n is monotonically increasing in n. All right, and one more condition coming up. So the function u, even though it is defined on the original given interval from 0 and capital T, but it satisfies the Navier-Stokes equation only up to the stopping time. So that's the definition of my strong solution. And then the result is that you may not feel comfortable with this notation. I may be abusing the notation because this is a random time. What I mean is actually, do I have chalk? If you are not happy with that, then what I mean is that actually this may be better. And like this. Okay, that's the one I mean. U is a progressive measurable function, so this is well defined. Okay, so so solution exists here, and I have an estimate of the stopping time. Of course, I'm only interested in small delta. If you look at the right-hand side, probability is supposed to be non-negative. It can be 0, but it cannot be negative. So if delta is large, then the 1 minus something could be negative. Then it's pointless. It's a useless estimate. It's meaningful only if this quantity is less than 1. And so I'm only interested in small delta. As you see here, it involves alpha. I don't claim that this is the best possible estimate. It is only one possible estimate. And k is independent of u naught and delta, and of course it depends on the size of the initial data. So if delta is very small, then it's not bad. Yeah, of course, if k is very large, delta should be smaller accordingly. But anyway, as delta decreasing to 0, the right-hand side is increasing to 1. Okay, so this is a result of a local existence of solution. For the global existence, I have to assume very special form of random noise. So it's not a surprise. So why don't I review something very simple for warming up, for motivation to select what kind of a random noise I can have. It should not behave bad as we expect. Okay, so let me review the known results from stochastic differential equation. So I believe this form of differential, this stochastic differential equation, capital Y is a scalar function. Every textbook on the stochastic differential equation has this example. And the nice feature of this equation is that we have an explicit form of solution in terms of exponent. So using that explicit form, these are the well-known facts. If a is larger than 1/2 b squared, then yt goes to infinity almost surely. If a is less than 1/2 b squared, then it goes to 0 almost surely. This is interesting because suppose that b is 0, then we have a deterministic equation. The solution is simply exponent of at, right? So if a is positive, it just grows exponentially fast. Nevertheless, here a may be positive. A may be positive. As long as it's strictly less than 1/2 b squared, the solution still dies down, almost surely. And when a is exactly equal to 1/2 b squared, then the yt fluctuates wildly between arbitrarily large and the small values as t goes to infinity. Okay. Nevertheless, it's very intricate. This doesn't mean that the natural energy dies down. Oops, excuse me. If you compute the usual mean square energy, it has this form, and you see, b squared doesn't do anything good. It only makes things grow. It does not contradict the Fatou's lemma. It's an example of Fatou's lemma with a strict inequality. Okay? Yeah. All right. On the other hand, let me look at this a different kind of noise. Here, a is a positive number. Epsilon is a small positive number. And think about this. I don't believe there is an explicit formula of solution, but it is known that in this case, no matter what a is, it doesn't matter. We have this. As long as the epsilon is different from 0. It's pretty bad. So I don't expect general random noise can still provide some kind of dissipation mechanism. But I need the previous type. I need this type, multiplicative noise, where p is different from 0. So I would say that it's non-degenerate multiplicative noise. So this is warming up. Oh, by the way, in this case, what happens to the mean square energy is this. It's not bad, right? It's bounded as t goes to infinity. All right, so what's the result for global existence? Oh, by the way, because of this warming up example, I need a more assumption. The previous assumption was global Lipschitz continuity on Fj and the Gj's. This time I need this condition. I still allow Gj's, but it better behave nicely. So I need this, and then you might wonder, hey, wait a minute, it looks very restrictive. The two conditions are compatible? That's the first question. The answer is yes. Just to think of a special, very extremely simple situation. Maybe I'll move over here. Just to think of some scalar times u times single Brownian motion. Good enough. So as long as a is different from 0, I will simply take eta 4 and eta 5 as just a square. And then I have no problem in satisfying this condition. But I need a to be different from 0. Okay? All right, so if I have this condition, then this is the result.
So you really have inequality largely equal eta 4, yes?
Excuse me?
There is no mistake in your first inequality. It's really
No, not at all. Not at all. So the result is, you give me any arbitrary small epsilon, then there corresponds another small number, depending on epsilon, so that if the initial condition satisfies this condition, then the probability that the sample path exists globally is larger than 1 minus epsilon. So this is the result. All right, so it don't take that much, but in the remaining time, I will very briefly outline the general strategy. The work is full of very boring technical estimates. I have no intention to torture you with these boring estimates. Instead, I will briefly touch on just the general procedure. Okay, so for the local existence of solution, as I already mentioned, the basic tool is a cutoff function. So this is my favorite approach. When you have a multiplicative noise, it generally is nonlinear. So what I do is, I first assume that the noise is given. It's a given function. Then what I do is that I regularize it. But I don't dare to regularize with respect to time variable, that you get something different when you pass to the limit. So, but you can still regularize it with respect to space variables. And then, time-wise, it's still bad, but with respect to the space variables, it's nice. So instead of a random equation, I can essentially reduce the original equation to the deterministic equation. So for each sample point, I can solve the deterministic equation by introducing new variable. I put together original unknown function u and random noise function together. Okay? And then the Brownian motion goes away. It disappears. But of course, then how do you treat the remaining nonlinear terms? It's not that bad. The time derivative only occurs in the first term, and the remaining, the garbage term, well, Laplacian is not a garbage term, but the remaining terms don't involve derivative with respect to time variable. So I don't have to worry about it. And as long as I just regularize with respect to space variables, random noise is not bad. It's a continuous martingale, right? A continuous function with respect to time variable and with a lot of space regularity because I've regularized it. So if the nonlinear term, even though it involves the differentiation with respect to space variables, it's absolutely okay. So that's the reason how I obtain the solution of a deterministic equation. So this psi n will play the role of cutoff function. So V is a new unknown function. As I just mentioned, it is defined to be u minus m. So m is the stochastic term, okay? And the stochastic integral of the right-hand side when the noise is given. And then where this corresponds to u and this corresponds to gradient of u, where u is the original unknown function. And then with respect to new unknown function v, I arrive at this form of equation. Here, the script A is a Stokes operator, Laplacian with a projection operator in front of it. Projection to divergence free vector pairs. Okay? So this is the new form of equation, which is equivalent to the original equation. Yeah, of course, this is possible only after I regularize everything. And I solve it for each sample point. And then this is not a problem. And by the way, I have to explain my cutoff function is a little bit weird. Nobody in the audience asked yet, but I'm sure that somebody will ask it anyway. So this term is fine. But what is this lambda? Lambda is at this point a certain given real number. And why do I need it? What will happen is that I'm going to obtain the solution using the contraction mapping principle. And as you expect, you first get solution on a very small time interval. So you need to extend it, right? My problem is that this term is a non-local. So after I get the solution on each subinterval, I need to patch up. So then at the initial time interval, you don't need this, but the next interval, to patch up with the previous interval, this lambda square will be the integral of this guy on the previous time interval. So that I can proceed step by step so that I can patch up to make a global solution. That's the role of this lambda. So right now, lambda is just given real number. But later on, when I obtain the a priori estimates, I have to allow it to be a random constant. Okay? Let's see. So I solve it, and then after you do that, then rewrite the modified equation. Why do I say it modified? Because I have a cutoff function in front of a convection term, so it's not the same as the original Navier-Stokes equations. And rewrite the modified equation in terms of original unknown function. So the term capital M, which is continuous martingale, okay, is moves out of the time derivative, goes back to its original position. Then it's now stochastic equations. For the measurability, of course, you have to verify that the solutions depends continuously on the data. And then you obtain the necessary stochastic estimates. And you need uniform stochastic estimates independent of a regularizing parameter because you want to pass it to the limit. And that's a lengthy procedure. And then for the multiplicative noise, just a standard procedure. Either you use an iteration procedure or a contraction mapping principle. And then you get the solution. All right, so I avoid all the technical details. All right, so for the estimate of a stopping time, I will just touch on the real basics in a very elementary way and a very casual way. But it touches on the core of the procedure. So how do we get the estimate of tau? Tau is a stopping time, which is the limit of tau n. Suppose that xt is a certain norm, any norm is fine, with a unknown function of a certain evolution equation, stochastic evolution equations. So depending on whatever basic function class you use, just to take the norm, and the x of t is now scalar function. Scalar, well, stochastic process, scalar value, stochastic process. So suppose that I define the stopping time with this, and when this set is empty, I assume that it's infinity. And then the idea of obtaining the probabilistic estimate is this. Think of the set of all sample points, this inequality, it's a subset of this. So this means what? This means this. Limit of tau n is tau. I want to get the estimate of this guy. Tau n is monotonically increasing in n. So I have this inequality, and from this, I have this inequality. What about this guy? If you have appropriate estimates for x, then this comes, the probability of this guy is nothing else but the consequence of a Chebyshev. Is it Chebyshev or Chebyshev? How do you pronounce it? You know what I mean, Chebyshev inequality. Chebyshev or Chebyshev, I don't know. But you know what it is. So if you have appropriate estimate of this guy, then this probability follows easily. So that's how you obtain the estimate of a stochastic time. All right. Now finally, for the global existence, the issue is this. How do we capture the stabilizing effect of a special random noise under the previous assumptions? For the previous example of a very simple model equations, we use an explicit formula. But that's out of question here. We don't expect to use it. So how do we get it? How do we expose? How do we reveal the hidden effect of a special random noise? So again, I will just to present it very casually, work with a very simple form. So this time, capital X of t is square of some norm, the energy, natural energy, okay? The V is the unknown function of any stochastic evolution equations. So typically it's continuous in t. So X of t is a continuous scalar valued stochastic process. All right, you first need this identity. Sometimes it's not easy to get this because I need the exact equality, almost surely. But sometimes you can get it. So you first obtain this identity. Well, actually, to arrive at this identity, you already used the ethos formula, right? You already used the ethos formula. From this on, you use ethos formula one more time, but slightly differently. Here, the power r is less than 1/2. It's not just less than 1, it's less than 1/2. But eta is a positive number. Then with respect to x, it's a nice function. X is always non-negative, right? X is always non-negative. So it's a very nice function. Of course, it's a C2. So I can use the Ito's formula one more time. So apply the Ito's formula here. All right, so what's the big deal of this? Look at this term. R is less than 1/2. It's negative. It's negative. It's negative. But there's a lot of problem. It's negative. You see, this f of v is the garbage term. Usually it's a source of trouble. We have to control it, clean up the trash. So to control this guy, I need ammunition. Well, eventually I'm going to take the expectation, so don't worry about this term. It'll go away anyway. So the source of control of this term is here. R is less than 1/2. It's negative. However, so definitely it's something I gain, but in this world, nothing is free. If you gain something, you have to pay the price. Nothing is free. So I benefit from the fact that this is negative, but the price I pay is, look at this power. What happens is that sometimes you don't need the eta to be small, but most of the time you want eta to be very, very small. And in my case here, I actually want to pass eta to be 0. So I have a negative power here. I can't pass eta to be 0 in general. No way, right? So how do I handle it? Well, if this guy provides extra power of x squared, that's what I need, then I can safely pass eta to be 0. Okay? It's bounded. So I need a source of extra power x here. That's exactly the reason for the assumptions I made. Okay? So that I can take the expectation this guy is controlled by this guy, but for the actual estimates, 2 different stopping times pop up and some technical complications appear, but that's the basic idea. Well, I think I already said everything I wanted to say. So maybe it has been too short talk, but yes.
I want to mention something. This technique is called in literature, or it is used in literature for noise stabilization.
Mm-hmm.
Exactly to use, in fact, Ito formula with subunitary formula.
Mm-hmm.
It is well used, in fact, to stabilize ODE and PDE. This technique of exactly you mentioned there. For noise stabilization. Here is, of course, not stabilization. You need stabilization for to have because you take, in fact, initial data in a small origin. But it's something different here. Perhaps you need to use here, because if you have an Navier-Stokes equation, only the first modes are unstable. The rest are stable. So if you separate the equation, you write the equation in 2 parts, finite dimension which is unstable, and infinite dimension which is stable, you can get the same result, sharp result.
Oh, I see. Okay, yeah. Yeah. I'm aware of that partition into different modes.
Yeah, sure.
Yeah, but I'm not that familiar, and I didn't even attempt to go in that direction. Yeah, surely, yeah. I won't be surprised if somebody can get improved result by going that way, because I've not even attempted to use it. Yes, thank you for your comment.
You didn't speak about this, or at least I haven't noticed. How do you use this inequality from below on your noise? Where this
You mean the assumptions on the FJs and GJs for the global
Yes,
UJ
that's
system?
right.
Yeah, right. When I try to control this garbage term using the last integral,
because then this inequality from below.
yeah, right. And the magnitude, this is a negative sign, so its magnitude, absolute value of it, is reasonably large in order to control this garbage term.
This way.
Yeah, on that process, the previous conditions intervene. Yes.
I was just going to comment on the last comment. I mean, it's not clear that in 3D you could do
Yes.
that type of splitting, because in the high modes aren't stable, really. I mean, the 3D estimates, it doesn't, you can't get that kind of stabilization for high modes, I don't think.
Oh, is that right?
I'm not sure that in 2D that would work, but in 3D, I mean, I think that's kind of part of the problem, right? This equation is morally like, you know, x, it's morally like x dot equals minus x plus some constant times x squared.
Mm-hmm.
And the minute you leave a tubular neighborhood of 0, you're in trouble, right?
Yeah.
All right, so that's even true for the high modes, I think.
Well, actually, I was not aware that that partition didn't work 3Ds. Yeah. But thanks for information.
Okay, so if there's no more questions, let's thank all the speakers again.
Thank you very much.